Alright, hi, this is Evan Vandenberg here, and we're taking a look at problem 66 from chapter 26 for Professor Bensky's Physics 133 class. The picture to the left kind of shows all the givens for the problem set, and then we're going to try to find, there's three different parts of this problem. A, what are the three fields created by the charges? So we've got to find E1, E2, and E3. B, do you think the fields obey the principle of superposition, which basically means does E net equal the sum of all the other electric fields? C, if E net does follow the principle of superposition, what is E net? Okay, so before we jump into part A, I'm going to just show a different picture of the givens with some geometric assumptions made. So to find the distance between Q1 and the point A, we use a Pythagorean theorem to do 3 squared plus 1 squared, which equals 3.16 centimeters is the hypotenuse of that triangle. Given the equal distances of Q1 and Q3 from Q2, you can assume that both the angles are going to be the same and that the distances are going to be the same as well. And then you can see here that we're also making the assumption that all the charges are pushing point A away from its given position. Also, to find theta, we just did a simple tan inverse of 1 over 3, which are the distances here and here, and we came up with an angle of 18.43 degrees. Okay, moving on to part A. Part A is asking us to find the electric fields of each created by each of the given charges. So we'll start with E1, which is derived from Q1. Right here it is 1 divided by 4 times pi times the permittivity constant, which looks like E naught there, or sigma naught. And that's multiplied by charge 1 over the radius squared times the unit vector of the radius. So here you use 9 times 10 to the 9th times our givens, which is 1 nanocoulomb, 1 times 10 to the negative 9th, over our radius, which is the hypotenuse of that triangle we found in the first section, squared. And you have to keep everything in their basic form, which is meters, coulombs, and in the value of Newton meter squared per coulomb squared. Okay, and then the unit vector here is going to give you an I and a j value based on that 18.43 degrees. So if we take a look back at the triangle, it's kind of easy to see where these come into play. The degree right there, and you get your cosine and your sine inverse, and your sine. They give you your I, which is your x component, and j, which is your y component here. So if you multiply that all out, you end up with 8.54 times 10 to the third nanocoulombs in the x direction, and a negative 2.85 times 10 to the third in the j or y direction. And this is pointing down because, as you can see in the picture again, if we take a look, you got E1 going below the x-axis, so that's going to give you a negative y component. Alright, moving on to E2. E2 uses the same basic formula. Keep in mind, E2 is a horizontal line, so it contains no y component, so all you have to do is multiply by the unit vector I, and this comes out to 1 times 10 to the 4th I newtons per coulomb. Thank you. Alright, and E3, we're not going to go through the math again. It's the same magnitude as the E1 electric field. However, the j component is positive since it's opposite. So everything's equal, just the j component is flipped since it's going up instead of down. Here, we keep the same numbers as E1. However, the j component is positive, as you can see here, denoted by the positive plus sign here. Okay, moving on to part B. Do electric fields obey the laws of superposition? The answer is yes. The electric field at a given point in space is equal to the vector sum of all the electric fields caused by their individual charges. So E net does equal E1 plus E2 plus E3. Alright, now let's go ahead and find E net. E net equals, as we said before, the sum of all the vector charges. So here we have all of them lined up in their I and j components. You combine like terms using simple algebra. The i's, add all the i's together, add all the j's together, and in this particular problem, the j components or y components actually cancel out. So you're left with just the sum of the x components, so that the electric field is moving in the positive x direction at 27.09 times 10 to the third newtons per coulomb. Alright, that's the problem. Thanks.